Half-life. Radioactive decay is a random event. We've no way of knowing when a particular nucleus will decay. However, we can work out when a certain proportion of the unstable nuclei will decay. We can model this behaviour with dice. We have no idea when one die will give us 6, but if we throw 600 dice, we'd expect roughly 100 sixes. Here, for simplicity, I have given the cubes one blue face. I'll refer to this as the blue face or sometimes as a 6. If we take a large number of dice, record how many we have, then throw them, we remove the 6s, or blue side up as I said, and repeat several times, the dice represent the unstable nuclei. A 6 represents a decay. A throw represents an interval of time. Unstable nuclei will decay if we just leave them. Dice would not suddenly turn over and give a 6. We can plot a graph of the number of dice remaining on the y-axis against number of throws on the x-axis. We end up with something like this. Here we can see that we started with 600 dice, and at half that number, 300 dice, we had this number of throws. So we can say that this is the time it took to drop to half our original number. From 0 to 3.8 throws is 3.8 throws. So we can say the half-life of dice is 3.8 throws. We could have a different starting value, for instance 500 to 250. That is this gap, which goes from 1 to 4.8 throws, which is again 3.8 throws. A different starting value again of 400 dice, half of that is 200, and this gap is now from 2.2 to 6 throws, which again is 3.8 throws. Whatever the number of dice we start with, we lose around half of them after 3.8 throws. We could say the half-life of dice is 3.8 throws. With radioactive isotopes, we've no idea when a particular nucleus will decay, but if we have a large number, the time taken for half of them to decay will be constant. It will take the same amount of time for half the nuclei to decay, whether we start with 10 billion, 8 billion or 5 billion. The half-life is the time taken for half the unstable nuclei to decay. We cannot say what the life will be, because as we get to small numbers, the random nature has more effect. In the same way, if we throw 600 dice, we expect roughly 100 sixes, but cannot predict when our last die will land on a 6. To calculate half-life from a graph, simply pick an initial value on the y-axis, draw a line to find the corresponding time. Usually we could start at t equals 0. Do the same for half that value. This then gives the time difference between these, which in this case is 0 to whatever this time is on the x-axis. You could repeat with a different starting value and mean the 2 or 3 half-lives found. So we could have these values or these values. Sometimes problems are set in a different way. For example, a 16 microgram sample of a radioactive isotope has a half-life of 2 hours. How long will it be before only 2 micrograms remain? Well, for this we can do a chart with time and mass remaining. We must remember to start at 0, so at 0 we had 16 micrograms. After one half-life of 2 hours, 16 will have halved to 8. Another half-life takes us to 4 hours, halving 8 takes us to 4. Another half-life takes us to 6 hours, halving of 4 takes us to 2. 2 micrograms is what we were looking for, so the time taken is 6 hours. As the number of unstable nuclei halve, the mass halves, as in this question, also the activity halves. So you can use this method whatever you're given in the question. Make sure you start with the time at 0 and remember to halve the property each time, not reduce the same amount each time.